Hi, my name is D.S. Eliot, and I'm going to show you the prime harmonic number sequence. It is a sequence that I invented, and it has no purpose other than being mathematically beautiful. So here I will commence with the drawing of the sequence. So first, I want you to know what a prime is. You may not know what a prime is. Now, let's say that a line segment represents any number. Okay? Right now, the way I've drawn it, this line sequence is divided only one time. So there's only one factor. Now, if you do this to it, that means that this number is divisible by 2. If you do that to it, it means that the number is divisible by 3. And I'm not going to go too far into that. So let's look at the numbers, the ordinary sequence of numbers. We'll start with 1, just because 1 is the first number. So 1, indivisible. 2, divisible by 2. 3, divisible by 3. And I'll write the numbers here. Now, here's where it gets interesting. 4 is the first composite number, which means that it is divisible by 2. So it gives you a reflection of what's going on up here. But then, within each unit, you can also do this again. And so 4 is 2 times 2. 3 is just 3, 2 is just 2, and 1 is just 1. Most of the time we forget about 1 because it is not very useful when it comes to talking about primes. Now 5 is also an interesting number in that it cannot be divided by anything less than itself. Yeah, that's 5. So 5 is just 5. 6 is a really great number because it's the first one that uses 2 factors. 6 can be divided by 2, and then each segment that the 2 makes can be divided by 3. And so 6 is 2 times 3. 7 is just like 5, 3, and 2 in that it cannot be divided. But I'm not going to obsess over that right now. 7 is just 7. So we can skip all of this segment thing. The point of it was just to illustrate what a prime number is. Now see, 5, let's show a little bit more what a prime number is. So this will be 5. 1, 2, 3, 4. We'll just say that's good. So this is 5. 5 is a prime number, which means that it cannot be divided by any lower numbers. If you try to divide 5 by 2, it cuts this center one in half, and you can't have that. You try by 3, and it's going to cut these two into parts. You try it by 4, and you get the exact same problem that you had before. Try it by 5, and you get the exact same thing that we already have drawn there. So 5 is only divisible by 5. And of course, everything is divisible by 1. So that makes 5 prime. Whereas with 6, we can divide it by 2, and then we can divide that by 3. Or we can divide 6 by 3, and then divide each of those by 2. And that makes it composite. With 6, you've got 2's and 3's. With 5, you just have 5. And so let's move on to the next part. Assuming that you understand prime numbers now. Okay. So let's go back to the ordinary counting sequence. We'll start with 2 because I don't care about 1. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, oops, 17. We'll go to 17. Now, what I'm going to do is give you the prime factors of each one. The prime factors of 2 are 2. Prime factors of 3 are 3. These are primes. 4 is 2 times 2. 5 is just 5. 6 is 2 times 3. 7 is just 7. 8 is 2 times 2 times 2. 9 is 3 times 3. 10 is 5 times 2. 11 is just 11. 12 is 2 times 2 times 3. 13 is just 13. 14 is 2 times 7. 15 is 3 times 5. 16 is 2 times 2 times 2 times 2. And 17 is just 17 because it's prime. We can see all of the primes only have one factor. 2, 3, 5, 7, 11, 13, and 17. Those are the primes. Now, what I realize is it gets a little bit cumbersome writing it like this when you get up to numbers like 16 because you've got to write 4 2's. So I just think we should take that number 4 and use it somehow in order to write these numbers. So I'm going to rewrite it all in terms of exponents. So here we'll just call this counting. Counting. And we'll call this factors. And we'll call this exponents. So 2 is 2. 3 is 3. 4 is 2 squared. 5 is 5. 6 is 2 times 3. 7 is 7. 8 is 2 cubed. 9 is 3 squared. 10 is 5 times 2. 11 is 11. 12 is 2 squared times 3. 13 is 13. 14 is 2 times 7. 15 is 3 times 5. 16 is 2 to the 4th. And 17 is just 17. Now, I have come up with a third way of writing these down, these factors. And it's not really that original of an idea, but, and I'm sure other people have come up with it before, but I call it the prime factor base. And so the prime factor base works just like I was showing you before with these bracket things. You have three there, 2 there, and 1 there. This is the 2's place, this is the 3's place, this is the 5's place. So when you write out a prime factor number, okay, I'll just write one out. So 107902. Okay, so this translates into the exponents form in this way. So these all go down and you have 2, 3, 5, 7, 11, 13. These are simply the primes listed out to the left. You take this number and you put it into the exponent, and you multiply them all, by the way. Multiply them. You take this number, put it in the exponent. You take this number, put it in the exponent. This number in the exponent. 7, 0, 1. And so this is the prime factor base. In prime factor base, 107,902 becomes 13 times 7 to the 7th power times 5 to the 9th power times 2 squared. And so every number has its own prime factor base equivalent. I'll show you. So 54, for example, is, let's see, 8 times 7? Yes. No. It's 9 times 6. Yes. Right? Crap. Alright, well, we'll just do 56 because that's 8 times 7. 56 is 8 times 7. 8 is 2 cubed. So 56 is 2 cubed times 7. In the prime factor base, this would equate to 3, 0, because that's 3, 0 because that's 5, and 1 because that's 7. So 56 in base 10 is 1003 in prime factor base. And so I'm going to write out this ordinary sequence of counting into the prime factor base. 2 becomes 1. 3 becomes 10. 2 squared becomes 2. 5 is 100. 6 is 11. 7 is 1,000. 8 is 3. 9 is 20. 10 is 101. 11 is 10,000. 12 is 12. And I love that. The 12s always line up for some reason when it comes to this sequence. It's beautiful. 13 is 100,000. 14 is 7 times 2, which is, you put a 1 there and a 1 there, 1001. 15 is 3 times 5, so that's 110. 16 is simply 4, and 17 is 1 million. And so we have changed the ordinary counting numbers, 2, 3, 4, 5, 6, 7, 8, 9, to a different way of looking at it. 1, 10, 2, 100, 11, 1000, 3, 20, 101, 10,000. It's very odd. So I want to look at this sequence and then compare it to another sequence which I have created, which is the Prime-Harmonic Sequence. Okay, so first I'm going to write out the counting sequence. And yes, I got a new marker, so this one will be working better. Okay, so what I'm going to do for this is I'm going to put them all in the prime factor base, and I'm going to give it 4 digits because that's just what I'm going to do. So 2 is 0001. 3 is 0010. 4 is 0002. 5 is 0100. 6 is 0011. 7 is 1000. 8 is 3 with 3 zeros before it. 9 is 20 with 2 zeros before it. 10 is 101 with a 0 before it. 11 is off the chart, but that's okay. 12 is 12, always. 13, again, off the chart. 14 is 1001. 15 is 0110. 16 is 0004. And 17 is 1 million. Okay, so we'll forget about these. Let's just go up to there. This is the ordinary counting sequence. And now I will reveal to you the Prime-Harmonic Sequence, and we will compare what they look like. So Prime-Harmonic Sequence next to that. So in the Prime-Harmonic Sequence, you do, of course, start with 0001, and then 0010, and then 0002. So it looks just like before. And let's, just for clarity's sake, let's write the base 10 over here and over here. So we'll have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, that looks a little bit sloppy, but whatever. Over here we have 2, 3, 4. So far it's 2, 3, 4. And that makes sense because that's what ordinary counting is. But after 4, for some reason, I decided to make the next number 6. And then after 6 comes 9. And so let's look at that. Let's look at what that looks like in the prime factorial base. So 6 is 0, 0, 1, 1. 9 is 0, 0, 2, 0. Now look at that. Look at here. We have one factor. It's the total number. If you add all of the numbers up in each line, here it's just 1. You have 1, and then you move it over. And then suddenly you have 2 factors. So you start with 2, you take one of those and move it over, and then you take another one of those and move it over again. So I will continue now. After 9 you have 5, 10, 20, 15, 5, 10, 15, 25. And you might think, well, that's weird. Why 5, 10, 15, 25? Why not 5, 10, 15, 20? The answer to that is, look at it this way. 5, we'll start with 1. Go by the smaller primes. 5 times 2 is 10, 5 times 3 is 15, 5 times 5 is 25. So every time you put a prime down, you are then dealing with harmonics of the other primes. So what does 5 look like? Well, 5 is 100. 10 is 101. 15 is 110. And 25 is 200. Now, if we look back over here, it doesn't look very orderly. It looks a little bit random, like it doesn't make sense. But over here, it does make sense. It's more orderly. See, you start with 1, 0, 0, and then the next thing you can do, well, you can't do anything because you've already worked with these 3 primes. You already had 10 and 1, so you have to add a new factor in. And so you add it in on the right, and the next thing is obviously just to move that factor over to the left. So you do that and you get to 200. And it has a sort of symmetry to it. So now I'm going to move on to the next part so that we can compare some of these other symmetrical things. So the next number is 8, and then 12. And look at this. This 12 lines up with this 12 lines up with this 12. The 12s are all aligned. In the prime factor base of 12 is 12. And the prime harmonic sequence 12th number is also 12. And 12 in prime harmonic base is also 12. So I just think that is wonderful. And I might as well write 8. 8 is 3, 0, 0, 0. Next is 0, 0, 2, 1. And I'm actually better at counting in the prime base than I am in base 10 because it's actually much easier. And so this is 18, this is 27. And then I wanted to briefly talk about what's going on here. Here and here. And here. So there's an interesting pattern. You can kind of worry about these ones later. There's an interesting pattern here that I kind of want to write out differently. So we'll do it like this: 2, 3, 4, 6, 9, 8, 12, 18, 27. And it goes on 16 there, 81 there. You take 16, divide it by 2, and then multiply it by 3. It's 8 times 3 is 24. You take 24, divide it by 2 is 12. Multiply it by 3, and that's 36. Take 36, divide it by 2, which is 18. And then multiply by 3. 18 times 3, what is that? 54? I think it's 54. Yeah. Okay, so what does this look like in the prime factor base? Okay, so you have 1, or I'll do it with two digits. I'll do it with 2 digits. So you have 0, 1 and 1, 0 at the top. Then you have 0, 2, 11 and 2, 0. Notice the symmetry. And then you have 0, 3, 1, 2, 2, 1, and 3, 0. And then you have 0, 4, 1, 3, 2, 2, 3, 1, and 4, 0. Note the symmetry. We start with all the factors on the right, and we move until all the factors are on the left. Also note, oh, never mind on that one. I lost my train of thought. So now I'm simply going to write out the prime harmonic sequence in the prime base ad nauseum, because I like doing this for some reason. First is 1, 10, 2, 11, 20, 100, 101, 110, 3, 12, 21, 30, 102, 111, 120, 201, 210, 300, and I'll start up here again. After 300, we have maxed out 3 factors and 3 primes. So we have to go to the 4th prime. And we go first to primes and then to factors. So we go to the 4th prime, and then we have to work our way up to 4 factors. So the 4th prime is 1000, which represents 7. Then we have to work our way up to 4 factors. After that, we can move on to the 5th prime. But first, you have to work your way up through the number of factors. So you go, there's 1 factor in 7. The next one has 2 factors. That's going to be 7 times 2, or 1001. The next one, because there's a priority of the highest prime over the number of factors, instead of adding another factor, you now have to bring all the primes to the left side. And so you do that by this: 1010, 1100, 2000. Now you have to add another one. Now you're at 3 factors. So you go to 1002. 1 and 2 add up into 3. So now you're going to repeat these old sequences, 2, 11, 20. And these repeat over and over in this thing. Remember, there's 2, 11, 20 and 3, 12, 21, 30. See, we can look at it this way. You see 2, 11, 20 here, and then 3, 12, 21, 30 here, and then 2, 11, 20 again, and then 2, 11, 20 here. So I'm just going to go faster. 1, 1, 0, 1, 1, 1, 1, 0. Now here, 2, 0, 0. Here's where it gets a little confusing. What do you do next? Well, you go to the smallest next thing that you can, and that's that one. 2, 0, 1, 0, 2, 1, 0, 0, 3,000. Finally, we have worked our way up to 4s. See, we had that, we had that. Now we're going to have the fourth one, which starts out with 8. 8 being, or no, sorry, 16, because that's 8 right there. 16 is 4. 4, 13, 22, 31, 40, 103, 112, 121, 130, 202, 211, 220, 301, 310, 400. And remember, we now have 4 places. So the next one is going to be 1003, 1012, 1021, 1030, 1102, 1111, 1120, 1201, 1210, 1300, 2002, 2011, 2020, 2101, 2110, 2200, 3001, 3010, 3100, and 4000. And so we have completed the four cycle, which is right. It's from there to there. You start with 4 factors in the lowest position and 4 factors in the highest position with 4 primes. And you go through all of the combinations between it. So here wait, where does it stop? There. So here, and what's the other one right there? So you've got 2, 11, 20 is the first, and I'll do the number with a line over it, is the notation for this. Okay, so 2, 11, 20 is the 2 sequence. 3, 12, 21, 30, 102, blah, 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 all the way up to 300 is the 3 sequence. From 4 to 4,000 is the 4 sequence. 5 would be from 5 to 50,000. 6 would be from 6 to 600,000. 7 would be from 7 to 7 million. And you capture all the numbers in between. Now, the only parts of this which are not like this are, we could call this the 1 right there. But then you got these in here and this one here. What do we do with these? Why are they in there? Why don't we just go 2, 11, 20, 3, 12, blah, 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 and then 4? Why don't we just do the 2, the 3, and then the 4? The reason is because right here, you've added in a new prime. And so you now have 3 spaces. You have 3 spaces. You've added in a new prime. And so there are now numbers which have the same highest prime, but a lower number of factors than that number of primes. So this is the 3rd prime. So when you get to the 2nd prime, you now have 2 places, and you can use 2 factors, which is why the next number is 2. When you get to the 3rd prime, you don't go straight to 3 because you've got to fill in these partial sequences. Basically, you're continuing this one. It should go 2, 11, 20, 101, 110. And I actually missed one. The next one is 200. I missed 200. So it should go 2, 11, 20, 101, 110, 200. And then after that, from 200, it goes here. It goes 2, 11, 20, 101, 110, 200, 1001, 1010, 1100, 2000. After that would be 10,001, 10,010, 10,100. But we have to fill in these. We have to fill in these here because it's really hard to explain. All right, so I'm going to shorten the whole thing because it is a very tedious process. I'm going to shorten the whole thing. So first we have 1, then we have 10, and we just keep those there. But after 1 and 10 comes the 2 with a line over it, and that shortens it. 2 with a line over it is 2, 11, 20. It is this. That is 2 with a line over it. After 2 with a line over it comes the next prime. So let's do it an even different way. We'll write prime 1, prime 2, let me just do this over. We'll write prime 1, prime 2, and then 2 with a line over it, prime 3, which would be 100. Now after prime 3, this is where it gets a little bit hard to put it into a thing, because after prime 3 you're going to have 101, 110, and 200. After that, you move on to 3 with a line over it. And After 3 with a line over it is complete, you move on to P4. Okay, I apologize for this video being very sloppy, but that's just what you get. I mean, later I might be able to do this less sloppy, but I'm not going to do that now because I don't have enough time on my hands, and I'm just going to power through it. Okay, so what I did before was kind of a partial way of doing this. I'm going to do it in the better way that I figured out. So this deals with a notation of P for prime, and then what were the letters that I used? Okay, so P is for prime, H is for highest prime factor, N is for number of prime factors. And so we will write out the sequence in a much shorter way. So we start with P11, which means the highest prime is the first one, and the number of prime factors is 1. And so P11 is 1 in the PFB, prime factor base, which is 2 in base 10. So after P11, you move on to P21. P21 is the highest prime factor is 2, and there's only 1. So that would be 10 in PFB, and that would be 3 in base 10. After P21, you fill up the 2's, so you go to P22. P22 equals, well, P22 is the entire sequence of 2 with a line over it. So P22 is 2 with a line over it, which is 2, 11, 20. But we will forget that and just say 2 with a line over it, because that's what I already established in this video. So P22 is 2 with a line over it, which is 4, 6, and 9. But we are going to forget about these because it's going to get too complicated. So after you fill up the 2's, you go to the 3's. You go P3, 1. So the third highest prime with only 1 prime factor, that gives you 100, which gives you 5. P32 is another sequence. The sequence is 101 to 200. P33 equals 3 with a line over it. That is 3, 12, 21, 30, 102, all the way up to 300. And then you move on to P41. And so let's write this out in the way of the original sequence in base 10. So 2, 3, 4, 6, 9, 5, 10, 25, 8, 12, 18, 27, 'What is next? So after 30 comes 102, which is 20. 102 becomes 111, which is 5 times 3 times 2, which is 30. 111 becomes 120, which is 5 times 3 times 3, 5 times 9, 45. 120 becomes 201, which is 5 times 5 times 2, which is 50. And then 5 times 5 times 3 is 75. And then you have 5 times 5 times 5, which is 125. So I now am going to show you how the new notation shrinks this sequence. So this is P11, this is P21, this is P22, this, oh, I missed one, shoot, forgot 15. This is oh, oops, I messed that up too. So this is P31, this is P32, and this is P33. So as you can see, a lot of space is saved with this new notation. P41 is going to be 7. P42 is going to have 7 times 2, which is 14. 7 times 3, which is 21. 7 times 5, which is 35. 7 times 7, which is 49. So all of that is P42. P43 is going to be a little bit more complicated, and honestly, I'm not even going to worry about it. And you get the picture. And so the simplified notation goes like this. P11, P21, P22, P31, P32, P33, P41, P42, P43, P44, P51, P52, P53, P54, and P55. And so on and so on and so on. Alright, so I wanted to talk about the lengths of these sequences. You might notice that P22 is 3 long, and P33 is a lot more. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. P22 is 3 long, P33 is 10 long. So I'm not going to go through the trouble of counting all these right now. I've already done it. Right now, I'm just going to write down the lengths of each of these things. So PHN, the N's go this way, and the H's go this way. So P11 is only 1 long. P21 is also only 1 long. All the 1s are 1 long, so I can just write 1s all the way down. And I only go to 6 because that's as high as I've counted them. They get really large, too large for my taste, too much counting. So the next one is P22. And P22, we've counted already, is 3 long. We've also counted P33, which is right here, and that's 10 long. But I have done my own counting before this video, and I know that there's a 3 there. And then I'm just going to fill it in. I'm just going to fill it in because why not? So this goes 4, 5, 6. Weird sequence. 3, 3, 4, 5, 6. Very weird. This one goes 10, 15, 21. This one goes 35, 35, 56. This one goes 126, 126. And this one goes 462. Now I could go on forever. Why would I? They are interesting sequences, but I'm not that obsessed with them. Now, a really amazing thing that I have discovered, and I'm not sure how I discovered it, is that there's a sequence in this that's related to the Pascal's triangle. And so I will show that to you. If you take these numbers, that sequence relates to, and it may actually also include that one, that sequence relates to part of Pascal's triangle. And I'll show you that in a second. So this is Pascal's triangle. Pascal's triangle is very simple if you don't know about it already. You start with, you can do it like this, but you can start with 1, 1. You add it together. You take, you might as well say that there's a 0 here and a 0 here. You say 2 equals 1 plus 1. 1 plus 0 is 1. 1 plus 0 is 1. 2 plus 1 is 3. 1 plus 2 is 3. 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 3 is 4. 0 plus 1 is 1. 3 plus 3 is 6. 3 plus 1 is 4. 1 plus 0 is 1. And so on. You keep going down and down and down. You add the 2 next to each other to create the one below it. And so my prime harmonic sequence contains this sequence of numbers, and these are the lengths of the P-N, or P, P22, P33, P44. These are the lengths of the sequence where H equals N. They go along this number pattern. And so we come over here, and where is that on here? And clear as day, it's right here. 1, 3, 10, 35, 126, 462. So somehow this sequence, and it's a weird one, because it's like right off center on the right, not necessarily the right, you could have picked the left, but it's right off center on one of the sides of the Pascal triangle. Every other line, those create the numbers here. And I have also just noticed that the other sequences exist in it very closely related to that one. So of course below this one is 3, 10, 35, 126, and that's exactly the same sequence. So we don't need to look for that one. But then the next one is 4, 15, 56. Might we be able to find that on here? And yes, it's right there. We could even include the 1. So 1, 4, 15, 56. This tells us that the next one in the sequence is going to be 210. So we can go ahead and put 210 down here. We can also put 462 here and say these are the 7s. Or no. But this is the 7th row. So what's the next ones? Well, 5, 1, 5, 21. Where's that on here? Oh, it's right there. So easy. What's the next one? 84. And then 330. So 5, 21, 84, and 330. What's the next row? Oh, it's just a 6. Well, we can just follow the pattern on this and continue creating it like that. So 6, 28, 120. So over here, you got a 28 and a 120. Of course, if I made this thing bigger, I could go on forever. But see, this right here, all this is Pascal's triangle. It's Pascal's triangle in a different orientation. How it's kind of difficult to explain exactly how that works. But anyway, let's keep continuing to fill this in. Since we have some numbers over here to play with, we can put the 7 there, and 1 there, and 1 there. We'll put an 8 there. After 7 comes 36. So 36. After 36 comes 165. And then we move on to the 8. After 8 comes 45, so we got an 8 there, 45 there. And then 9 and 55. And we ran out. But we can put a 10 here. And basically what I'm telling you is that the Pascal's triangle is the lengths of the prime harmonic sequence. Every single one of these numbers maps onto Pascal's triangle perfectly. And I find that to be mathematically beautiful. So it's based on primes, and it's also based on Pascal's triangle. So you take primes and Pascal's triangle, put them together, and you get the prime harmonic sequence. I just think it's mathematically beautiful. So the way that you do this is you draw a line down the center, which basically cancels out all of those middle values. It should cancel out that one too. And then you draw diagonal lines like this. And so what that will give you is you just take that, flip it around. You've got 1, and then 1, 3, and then 1, 4, 10, and then 1, 5, 15, 35, and then 1, 6, 21, 56, 126, and then 1, 7, 28, 84, 210, and 462. And that's as far as I got as far as getting all the values. I mean, best I can do with what I have right here is 1, 8, 36, 120, 330, and then 1, 9, what is that? 45, and then what is that? 165. Then you got 1, 10, 55. And then what else? 1, 11. That's all I can get. Basically, these lengths are exactly the same as Pascal's triangle. They are Pascal's triangle. The lengths of each subset of the prime harmonic sequence is simply Pascal's triangle. Okay, so I have chosen 4 numbers. I had to pick them because they fit in this. I couldn't pick numbers that don't fit in it, and I had to kind of think about it. But so these are in base 10, and I'm going to put them in PFB, prime factor base. 48 is 6 times 8, which is 2 times 3 times 2 times 2 times 2. That means that there's 4 2's and 1 3. Right? That would be 16 times 3. Does that work? Yeah, it does. 16 times 3 is 48. All right, 132 is going to be 33 times 4 is going to be 11 times 3 times 2 times 2. So 11 times 3 times 2 times 2. 450 in prime factor base. Let's see. That is 50 times 9. And that is 5 times 5 times 2 times 3 times 3. So 5 times 5 is 2. It's 25 times, okay, it's 50 times 9, so it's 25 times 18. So 25 times 18, and 18 is 3 times 3 times 2. So there's 2 3's and a 1. Okay, I think that's right. Let's see. 25 times 9 times 2. That's right. All right, 165 is, what is that? It's 11 times 5 times 3. Yes. 11 times 5 times 3. So 11 times 5 times 3. 1 0 1 1 0. All right. So what I had planned out doing was to take these numbers and find where they lie in this sequence. All right, so 48 is 14, which means that the highest prime is 1, the highest prime is 3, is the second prime. The highest prime is 3, which is the second prime. And so that means that, remember, we do P, H, N. And so H is the highest prime. The highest prime here is the second prime, so H is 2. So it's going to be in this row. The number of factors is 1 plus 4 is 5. So that means that it's going to be way out here. Oh, unfortunately, I didn't really think that through, did I? Okay, so what I figured out is that anything that lies out here, you just go straight down to there. So 48 can be found in P55, which is 126. And it's very easy to find it. It is actually the second number in the subsequence. So the first number is 5. The second number is 14. And then 23, 32. Okay, so 48 lies in P55. And it is the second number in P55. So in order to get the number that 48 is in the sequence, the cardinality of 48 in the prime harmonic sequence is 1 plus 3, 1 plus 1 plus 3 plus 1 plus 3 plus 10 plus 1 plus 4 plus 10 plus 35 plus 1 plus 5 plus 15 plus 35 plus 2. And that gives you the location of 48 in the prime harmonic sequence. Now we'll do 132. The highest prime in 132 is 11. Yeah, 11. So H is 5 because 11 is the fifth prime. So now we have to count how many factors are there. 1, 2, 3, 4. So N is 4. So the number is P54. P54 is 35. So 132 can be found within this 35 right here. Now, where is it within this 35? That is a little bit more difficult of a task to figure out. But it's not that bad. You start with, dang it, this stupid marker. Well, I guess this marker is dead. That's horrible. You start with 1003 or 10,003. 10,012. Well, it's the second one, just like before. So in order to find the cardinality of 132 in the prime harmonic sequence, you just have to add up all of these numbers. You get to that one. Instead of adding 35, you add 2 because it's the second number. All right, next. 450. 450 is 221, which means that the highest prime is 2, H is 2, so it's here, but of course we're going to end up going over. 2 plus 2 plus 1 is 5, which means that it is there, just like before. It is in it's in P55, 126. But 221 is a little bit further down the line, and I don't really feel like counting all the way to that. I do have to find a way of determining how to how to find it faster without counting all the way up to 221. But 221 is basically in the same, it's in the same sequence as this. It's just way down there. All right, 165. We'll find 165's cardinality. That is 10110. So the highest one is 11, which is the fifth. So H is 5. The number is 3, 1, 2, 3. N is 3, so it's P53. P53 is 15. So 165 can be found within here. The cardinality is all of these numbers added up until you get to there, and we can count to that one. It's pretty easy. You start with 1002. oops, there's 3. 10002, 10011, 10020, 10101, and 10110. And that's the number we're looking for. So 1, 2, 3, 4, 5. You count all of these numbers until you get to there, and then you add 5, and that is the cardinality of 165 in the prime harmonic sequence. Okay, I must briefly correct myself because I kept saying cardinality, and I think what I meant was ordinality. I'm talking about the count, the number that the number is. So, but I'm not going to go back and fix all my mistakes. Instead, what I'm going to do now is I'm simply going to write out the prime harmonic sequence in the two bases, in prime base and then in base 10. And I'm just going to fill the board, and then I'll be done with this video. So let's start. I'm going to do it in prime factor base first because it's much easier to do it that way. So let's start. 1, 10, 2, 11, 20, 100, 101. Okay, and see, this is P11, P21, P22, P31, P32, P33, we have reached the end of P33, so I'm going to just go over here and do P41, which is 1000, P42, 1001, 1010, 1100, 2000. P43 is 1002, 1011, 1020, 1101, 1110, 1200, 2001, 2010, 2100, 3000. And if you haven't figured out the pattern in this counting yet, then I mean, just look at it. It's actually very simple how this counting works. And then P44, because we reached the end of P43. P44 starts with 4, and I love it. It's so epic when you bring back this ordinary number like that. 4 becomes 13, 22, 31, 40. Start over here. 103, 112, 121, 130, 202, 211, 220, 301, 310, 400, and then we go up 1, 1003, 1012, 1021, 1030, 1102, 1111, 1120, 1201, 1210, 1301. No, wait. No. 1300. 2002. 2011, 2020, 2101, 2110, 2200, 3001, 3010, 3100, 4000. And finally, we have reached the end of P44. We're going to move on to P51, which is 10000. P52, 10001, 10010, 10100, 1000, 2000. P53, 10002, 10011, 1020, 10101, 10110, 10200, 1101, 1110. One more column and that'll be it. 1110, 1200, 2001, 2010, 2010, 2100, 3000. And now we do P54, which starts with 10003, 10012, 10021, 10030, 10010, 102, 10111, 10120, 10201, 10210, 10300, 11002, 11011, 11020, 11101, 11110, 11200, 12001, etc. That's it. That's all I'm going to do. Now we'll go through and put them in base 10, or at least try to. I'm probably not going to do the whole thing because it's too hard and I'm running out of time. So, and I'll do this in another color because it'll be less confusing. I'll use red. Okay, so 2, 3, 4, 6, 9, 5, 10, 15, 25, 8, 12, what is it, 18, 27, 5 times 4, 20, 5 times 3 times 2, 5 times 6 is 30, 5 times 3 times 3 is 45, 25 times 2 is 50, 25 times 3 is 75, 25 times 5 is 125. And then we have, what do we have next? 7. 7 times 2 is 14. 7 times 3 is 21. 7 times 5 is 35. 7 times 7 is 49. 7 times 4 is 28. 7 times 3 is 21, times 2 is 42. 7 times 9 is 63. 7 times 5 is 35, times 2 is 70. 7 times 5 is 35, times 3 is 70, plus 35 is 105. And I quit. That's as far as I'm going to go because I'm sick of this doing. I don't like converting back from prime harmonic or prime factor base. But anyway, this is the prime harmonic sequence. 2, 3, 4, 6, 9, 5, 10, 15, 25, 8, 12, 18, 27, 20, 30, 45, 50, 75, 125, 7, 14, 21, 35, 49, 28, 42, 63, 70, and 105. If you want to really confuse someone, give them the first 10 numbers of the prime harmonic sequence and ask them what the next number is. Ask them if they can continue the sequence. And that is a very, very difficult thing for people to figure out who have no idea. But the rules of this sequence are a little bit complicated and very hard to explain. So I think I'm going to end it there. And I really tried to explain it as good as possible. I think I said just about everything. The relation with Pascal's triangle is really what I think is like the deepest part of it. There's probably deeper things to it, but I haven't quite figured them out yet. So yeah, that's it. Thanks for watching.